Thank you so much. Thanks for having me here. My name is Rodolfo Monterroso. I'm here representing Pollution Control Technologies. We are a company based off of Laramie, Wyoming, and we're here to present XFA, which is an on-site mercury removal technology. And we'll briefly go into that. We'll go into that very soon, but I want to introduce a few other aspects of the technology before we get into that. As I said, we are a startup company based off of Laramie. So let's start on that. Basically what motivated this technology is that a drive at the University of Wyoming to tackle environmental regulations that affect coal currently. And so we started as grad students initially who were working on projects related to coal. So mercury and CO2, and that's how we started these ventures. So basically the problem is, as you all are aware, with mercury for coal companies is based off of MATS regulation. MATS was the mercury toxic standards, for those of you who are not all that familiar with the technology, was finalized in 2011. And it basically states up today that you have to comply with a certain limit, which is about 1.2 pounds of mercury per trillion BTU, and that has to be complied for all plants that are above 25 megawatts. And so that affects clearly Wyoming, because Wyoming is a big coal producer, and also due to the power plants present in Wyoming. What happened with that was that if at a time some plants were not able to comply with that regulation, they would either need to retire or change the fuel, or in the majority of the cases, change the strategy and implement new APCD, as we'll see in the next slide. So the majority of the plants either changed to the strategy to get more air pollution control devices, or would have to retire. So what happened at the moment was that at the moment of implementation in 2015, April 15, 2015, plants applied for an extension, and that allowed for an extra year, which has already been passed. So everyone right now who's above 25 megawatt producing power with coal is enforced to comply. According to the EIA, or this made quite a bit of closures estimated, or that they attribute to MATS. So there's definitely been an expense on MATS and closures due to this regulation. So I guess that our main goal here is to provide solutions that would cut the costs to comply with these regulations. So can we go to the next slide? Thank you. So these are the effects, direct effects on the in the coal industry of the mercury toxic standards. And as we can see, the majority of the plants either would have no change because they already had the air pollution control devices implemented. But on the other hand, there's quite a bit, as you can see on the graph on the right, that would implement our activated carbon injection systems. So it's definitely had an impact on the way it's been handled. And just to explain, this graph is all expressed, both of them are expressed in gigawatts. So that's the amount of gigawatts that have either implemented air pollution control devices, activated carbon injection, or other injection systems that would control mercury emissions. So just to briefly summarize, there's an economic impact in the coal industry based off of MATS. So let's go to the next slide. Okay, and then Wyoming, being clearly the biggest coal producer in the nation, has suffered a big toll on this, either due to the power generation, or because simply, coal is not going to be used as much, mainly because of the CO2 regulations, but also, of course, due to MATS. So we want to tackle that problem in a manner that's efficient and lean, mainly. So that's how we came up to the process that I'm going to describe very briefly. Soon. Let's go to the next one. Okay, so we are Pollution Control Technologies. We're founded in 2013. We're headquartered in Laramie, Wyoming. Initially started as a research and development company. We're still developing quite a bit of products. Mainly XFA is our target, which is what we'll discuss here. We have an active research lab where we do quite a bit of chemistry, characterize sorbents, develop new controls for CO2, for mercury, and our process is currently funded by a federal contract. That's our team. And then as I said, we're developing currently other technologies to control carbon dioxide. We're working with the University of Wyoming, the Western Research Institute, and currently working with Sask Power, which will allow us to test our Sorbent technologies. Our Sorbent is based off of the byproducts of the plant. And so I'll show you in a minute how this operates. Okay, so to talk briefly why we're here is to mainly talk about this process, which is called XFA. So XFA is a sorbent produced based off of fly ash. And that is, I don't know if, so if you're familiar with the process from a power plant, byproduct is ash. So we're basically using things that are already at the plant to reduce the amount of energy that's required to control an emission. So basically, right now, the current suite of technologies that's used to control mercury emissions is activated carbon and other technologies in place. Now, activated carbon requires coal mining, activation of the coal, and so that requires quite a bit of energy. Our process is basically differs from them in the sense that we are using the byproduct of the plant, which is ash, and we're activating it using a thin layer of an activator that goes around the surface of the ash and captures mercury. Can we go to the next slide, please? Okay. So the main difference with this process and other ones is that we believe it's sort of a very lean process that does not use much energy. It has a very, very small footprint. The whole process, since it's an on-site process, it utilizes a mixer that's connected to the plant in the sense that ash or the byproduct comes out of the collection of the storage of ash, goes into an activating station and occupies a space of only 6 by 6 by 6. And so then ash gets into our activation station that gets mixed with a solid activator and coats ash. This requires very low amount of energy, mainly 2 to 5 horsepower, even for a very large plant. So that is, the very small size, quite like that of an office at a plant. This constitutes a very fast and high efficiently coating process, which produces no byproducts and does not generate any waste. Let's go to the next one. Okay, so basically how do we do this? We take so out of all the production of ash, we take only a stream of 1% of the production, and that we coat with 1% of the activator. So basically the latent ash or the waste ash only has 0.01% of activator on top of that. So that means that the ash is not affected. It does not lose any of the properties. So for plants who actually sell ash to cement operators, there is no change. There is no interaction with air pollution control devices, materials that we've found. We've tested with ash that goes through different devices such as wet FGDs with SDAs, and the ash has had no problem. That means that also we were able to pass the different leaching tests and preserve ash for resale for cement operators. So those are some of the advantages of the process. Can we go to the next one? I just want to, next one, and then we'll go back to this. So basically what I wanted to show is mainly the process here. So as I said, basically what you need in a process like this is you need to have a source of the byproduct available that will go into the station that's where we have a low energy mixer, which is for the size of a plant is a very, very small mixer that will get mixed with an activator, proprietary activator, which is the whole process, the patent pending process. That creates a thin layer over a very short period of time, about 20 to 30 minutes, and then that goes re-injected into the flue gas stream. The new ash, which constitutes 1% of the weight of the ash, traps all the mercury, and so as you see here at the very end of the process, there is no mercury coming out. So we have the latent ash with mercury interlocked with waste ash, and there are no byproducts, and it's an irreversible capture. So we have shown leaching capable, passing the leaching tests and still keeping the mercury on site. Can we go back to previous ones? Okay, so the main advantages of this thing is since we're using less energy, we can cut the sorbent costs in half, have much less, no waste basically, because we're only putting 0.01% of the weight onto the ash of the original ash, so basically there's no waste. We can produce it on demand, so we can change the properties of the sorbent as compared to, for example, say activated carbon, in which case you would have to use the same product. And as I mentioned before, we're not altering the properties of the waste ash. Sorry, just can we go to the previous one? Previous? No, yeah, let's keep going. Yeah, let's go to next. Okay, so here are the outcomes of our research. This is what we obtained. We noticed that by trying this product at different settings, especially in a pilot plant facility, this can't be read here, but it's $1,400. We were able to achieve the same capture of mercury at $1,400 versus $2,800 with activated carbon. And that is scaled, also calculated for a 500 megawatt plant, injecting activated carbon at a common cost, which is about 90 cents per pound. And this also means that we had many other advantages, such as no waste in this process. We could inject at different temperatures as opposed to activated carbon has some limits to it. It has to be injected at a certain station. Usually it's not injected at a really high temperature, such as post or preheater or so, because of the physical nature of the process, whereas our process is more related to chemical capture. So we had a few advantages in that. And in the results of pilot plant, we achieved these numbers. Go to the next one. Okay, so here's a test that we ran against amended silicates, which is a commercial product available in the industry. And in this case, we achieved same level of capture at lower injection rate and also at a fraction of the cost, because amended silicates is a sorbent, commercial sorbent, that's actually more expensive than activated carbon. And so because of this, this would be a direct comparison to a commercial product that's been developed here by us that can do the same result at a much lower cost. Also, we compared, can we go to the next one? We compared this product to activated carbon, and in this case, we're shown here in the graph on the left. Here, if you see the line underneath, that shows the capture of XFA, which is our product. Basically, I'll just explain this very briefly. If you see the line at the top, that's the total mercury injected in that filter. So if you had a graph that would cover the whole thing, that would be 100% capture. In this case, we have the capture that's the lower you go, the more capture you have. So basically comparing the reactivity of both products, our product captured more. Here also we show on the graph on the right that we can tune our product to have more or less reactivity depending on the needs of the plant. So that's a difference that we have because our product is produced on site, so the amount of activator that we add depends on what's needed. So the points in this line show different sorbents that we had and what the total amount of mercury could be uptaken by such sorbent, whereas the black line refers to activated carbon. So if you see the red line, you could have far more capture. Sorry, the red line here, the only red line here refers to activated carbon, whereas our sorbent could be tuned to the necessity of the plant and have much more capture depending on what we want to do. So basically, this is the technology we're running. We're looking right now for different testing partners, which is part of the reason we came here as well. We have been able to work with different power plants such as Sask Power in Canada, and right now we're also trying to implement a test plan with Pacific Core and different power plants around the nation. So basically that is the goal of our technology at this moment. I don't know if anyone has any questions about this?
Very interesting. Can you go back and talk a little bit about when you say there's no waste product?
Yeah.
What that actually means, because it looks like there is still some, I mean, you're going to have the mercury removed from the process. And so if you could talk through what happens at the end with how much, mercury is still being released versus how much is removed, and then what do you do with those stuff you've removed?
So basically, the goal when you inject a sorbent is to comply with the regulation, right? Let's say, let me give you an example. An arbitrary number for native coal, let's say is 10, right? Which is, the number is 10 micrograms per meter cube for a PRB, as an average number. Now, when you inject, what you're trying to reduce is to the level of compliance, which let's say it's 80% of the reduction to meet MAT's regulation. So you'll still emit as much as it's permitted by MATS. That number I gave before, which is 1.2 pounds per trillion BTU. So that's what will come out. You can reduce all the way to zero, but it'll be more expensive. So plants normally reduce all the way to compliance limit. So you'll inject as much as you need to comply with MATS. And then mercury that's in the latent ash, what's loaded with XFA, will come out in the byproduct. So here, in this stream. So basically, where you remove ash, that's where mercury will be trapped, interlocked, and just as you do currently. That's what the current technology does, is they inject either dry sorbents or activated carbon, and that will go into the stream, capture mercury, and then deposit into the final ash. And so long as it's locked well enough that it won't leach out, then you are under compliance.
So then it remains in the final ash.
In the final ash.
But it's basically isolated and locked in, so it can't
Correct.
leach.
And Adolfo, maybe just clarify for some of the folks. Typical activated carbon changes the fly ash, so it diminishes its value for using in cement production, its resale value. Can you talk about how I believe your technology doesn't have that same effect on the fly ash and therefore doesn't diminish its value for cement production?
Absolutely. So, mainly one of the things I was mentioning, and let me go to a different slide here. Okay, so as I said before, the product itself, what's introduced into the activating station, has 1% of an activator. That is the product that we use to capture mercury. However, the total amount of ash that we use to produce that product, the XFA, is 1%. So we're talking 1% of the 1% is the amount of activator that's present on the final ash. So a 0.01% to 0.04%, which is a total amount, which is very, very small, compared to, for example, the amount of activated carbon you would inject, which, by the way, activated carbon has a property that can uptake air entraining agents for a concrete process. If you wanted to sell it to a cement plant, this would not happen with our activator because it wouldn't have that property to start with. And secondly, on a mass basis, you're using a lot less of the activator. Say, regardless of the amount of XFA that you'd be injecting, the total amount of activator present in the final waste is almost negligible. And so this does not change on any mass or volume basis the properties of the ash if you wanted to sell it to a cement operator. That's why there's a big distinction there, not only on a mass basis, but also on a chemical basis, because our activator is not it's not based off of activated carbon. It's not the same. It won't uptake, say, for example, what you use in a concrete production, which are air entraining agents.
Questions from audience?
All right. Well, thank you. Thanks for taking the time.